topic today is about crowdsourcing mapping. We will, as mentioned by Ricardo, we will have hands-on activity regarding the moon, but I would like to show you the possibilities deriving from the crowdsourcing. I don't know how much familiar are you with this kind of topic, but crowdsourcing has quite a lot of different names. It's called also citizen science, participative science, people-powered research, a bunch of terms. But if you want to really go into practical things, what does these terms mean? There are a couple of formal definitions I put here, but I would like to highlight that basically you are involving people who are not scientists and in a project that is led by a researcher, by a scientist. And the people helping you are varying, have diverse knowledge, diverse skills, and they collaborate with you in gathering data, gathering quite a lot of data. As we saw in the previous talks, you can have up to thousands or tens of thousands creators that has to be counted to get to data. You have to cover large areas. You need to subdivide the areas between different operators, and these maybe can be shortened by involving some other people. You have to think about the people who work with you, not as, let's say, workforce, not slaves, let's say, but just collaborative people. They are people that have no obligation to work with you. And so they have to be involved. You have to be collaborative with them. You have to involve them and to give them something to work with you. But is it really working? I mean, this can sound a little bit odd, a little bit theoretical. I did just a few research yesterday preparing the presentation, and as yesterday, just searching for citizen science on Scopus, you have up to 12,000 results. And as you can see here, is quite a young approach. I mean, the best cited, the free best cited is over 1,500 citation, and is date back to 2007. So it's a young approach, but it's an effective approach, both with numbers and citation. But here is the citizen science as a whole. You can approach it with biology, with economics, whatever you want. But let's try to be a bit more strict. If you want to tighten the topic to the physics, to the astronomy, to what we really do, you can see that you have up to 500 results. The oldest date back to 2007. I mean, it was not really effective. It had 0 citation, but it's the oldest one. And then the best cited is a project, a paper talking about a project led by NASA, and has up to 500 citations. So yes, we have this kind of approach is effective also in our topic. If we move forward, let's try to be a bit more specific. What about the topics of the winter school? If you look and search for Venus, Mercury, Mars, the Moon, okay, you can see there are very few papers about it. It means it doesn't work. In my opinion, it means that you have space for applying it. Because if you want to go to the best, to the largest community for research-based citizen science research, is called Zoe Universe, and it has up to 3 million people who register to contribute to the research. And the most successful project is called Galaxy Zoo, and as you can see here, is led by ESA, the European Space I can't remember the acronym, but yeah, is the European Association. And then you can go to the statistics. You have about 120,000 people contributing to this project. And this project is exactly what you have saw before, and also is summarized in this paper that gathers about 1,000 citations. So yes, it's effective. But what people do with citizen science? You can have a designed application that can be also GIS application, as we will do this in the next activity, or it can be designed especially for this. As you can see here, this one is the application that has been designed for the project Moon Mappers that count craters on the moon. You have here the tutorial with examples. You have possibility of tools that allows you to measure, to try to sketch all the craters you obtain. And then you have here the original image and the results after the mapping of all the volunteers. Of course, you cannot, not all the results are exactly true. This one here is the results after checking. What can you do? You can have, let's say, 100 people that map the same areas. If you have a minimum threshold of, let's say, 70% people marking a crater, then that crater can be considered a real crater and then checked by the researcher. But you have only to check the results gathered by someone else. You don't have to do the work on by yourself. So this is citizen science, let's say, at broad lines. But as mentioned by Ricardo, we will face boulder mapping. So what is boulder mapping? You have to identify and map boulders that lies on extraterrestrial bodies. Here you have an example for the comet 67P. I will not try to name this name, to pronounce this name. Let's say Churyumov-Gerasimenko, okay? And you have an approach to a circle of a boulder that is not a regular shape. But as you can see, this one is an uninterpreted image, is a raster image with a lot of boulders upon them. And this one here is the interpreted version. You go from a raster to a vector. So you can have, as shown before by Thomas, you can have a result of circles upon which you can do statistics and obtain some results that can give you a hint about the information that you want to gather. So why boulders? Because they are quite simple, let's say, but how do they form? What they give me information about? Commonly, you have boulder formation under not so quiet, let's say, circumstances. You have asteroid impacts, glacial advanced retreats, landslides, differential erosion. Of course, not all of these processes apply to every extraterrestrial body, but you may have all of these to form boulders. On the moon, you will face in the next activity, you will face boulders that formed after an asteroid impact, for example. And are they common enough to deserve our attention? Why I should care about them? Yes, they are common enough. As you can see here, you have examples from the moon, from Mars, from Ryugu, different bodies. You have a planet, you have an asteroid, you have a moon. And on all of these surfaces, you can recognize boulders. So yeah, they are quite widespread. If I get the technique, if I get the approach on a specific body, then I can extend it also to the others. And in the end, okay, I focused on the boulders. I discovered that they are common, but why should I care about that? I should care about that because they can give me hints on active morphological processes that are ongoing on the surface. They can also reveal underground materials. I will not go into details about this paper. I'm just giving you an overview of what you can obtain. You can also infer some hypotheses on the basis of the boulders' abundances and size frequency distribution about the origin of the bodies. And then, in the end, as said before, last but not least, they are fundamental for landing safety of landers and travel planning of rovers. If you have a lander that is about, I don't know, 10 cubic meter, and you have a surface that is scattered with boulders that are up to 1 or 2 meter high, then it's really sketchy to have a landing here. You can have rolling of the lander, crashing and everything that can vanify the efforts of millions of euros of dollars. A real waste of money. Anyway, if you want to cover the area of your interest, it may take a long time to cover it. As you can see here, this one is an example where a study gathered about 12,000 boulders. Here I was involved, also Ricardo was involved, and we were 6 people counting all of this, meaning that each one of us has about 2,000 boulders counted. It may seem a lot, it may not seem a lot, it depends on your sensibility, on your skill, but yeah, if you have, let's say, 100 people working rather than 6, then things are really easier and you can cover larger areas. As long as I have my map, you can build those kind of graph that was already shown before, the power laws, and you can go back to, you can infer the intensity of phenomena. For example, here, the cumulative size frequency distribution of boulders on the comet I showed before, the 67P, allows to infer the intensity of the degradation of the comet due to the solar influence. As you can see here, I mean, it can be quite logical, but this is demonstrated that the head is affected more from solar influence rather than the neck, whilst as an overall, the body has this kind of values here. And also for the safety, as in the graph before, you have an age that is inferred by the distribution of craters. Here you can have a distribution of boulders that, based on a sample areas, give you a hint of the distribution of the boulders over the whole area, a coverage of the area, let's say the number of the rocks per square meters. If you want to have some insight on this, we can talk about this later, but yeah, I'm just giving you some suggestions, some hints about what you can infer about this. So there was a question, or maybe about 2 questions about the errors before. In this case, we have, let's say, 3 main sources of errors. We have the adopted image and its characteristics, hair characteristic, resolution, lighting, coverage, noise. But yeah, we can say that this topic, this main source of errors can be studied, can be evaluated, because you have the resolution, you have the lighting, you can search for different images if you have any, or at least if you have just a little one, you can still at least evaluate your performance about that. Then you have the adopted guidelines, the workflow. Is it the task clear enough? I have defined well my target. I have defined what is a crater, what is a boulder. I have to map the interior, the exterior, the shadow. All of these aspects must be clarified in advance, because if I think about this during my task, then my mapping may change during time. And so you have to be clear. You have to define, to study the object. Here is an example of the boulder. I will go much more into detail about this graph later on. But as you can say, you have to define the main reference point to map your boulder, define it. And then in the end, you have the operator biases. Trying to summarize this in a single question, may I assume that acquired data are correct? As in the example before by Thomas, 2 operators, 2 different results, which one is in error? Are them both in error, or are them both correct, but they use different definition? Errors may also start from that thing that is called pareidolia. So the human trend to identify things that recognize on images that doesn't really represent that kind of things. Here you can see the famous face on Mars, but also a bear on the moon, or a door again on Mars, or maybe you can see faces on the beans. I mean, this is something that we all see, and it depends on how we are, on how we see the reality, let's say. And you may have noticed one of the problem about this. If I work with planetary geoscience, I have remote sensing, field surveys, research skill. Remote sensing, we talk about this. And of course, we don't have field survey, except for those rare cases where we have some lander, some rover that give us some data about that. But the main thing is the research skill. Especially if you are involving people that are not actual researcher, but they are people that are just enthusiasts, that are volunteering for your project. So your project needs to have some fundamental points. It must be useful and meaningful. It's not worth to invest money and time in something that will not give you some insight into science. It should have some high time-consuming tasks, because if it is something that is very specific, but it's not require much amount of time, it's not worth to involve many people, to invest time in involving them if they are not giving back an advantage for me. You have to gather an appropriate amount of helpers to do this. And the task must be manageable by them. Here is an example of an evaluation of public engagement and the contribution to science of different citizen science projects. As you can see, you want to be here, you want to engage a lot of people, and you want to have a very outstanding contribution to science. On the opposite side, if I having low public engagement and low contribution to science, then I'm somehow failing. And in the middle stand everything else. It depends on you, it depends on your project, on its characteristics, but you want to engage many people, you want to have a high contribution to science. And then you have to estimate their reliability. Here is a comparison of what have been mapped by a group of volunteers, that is the blue cap, the blue boxes, and what was the actual true results after a check by a trained researcher, that is the orange boxes. As you can see here, you have, let's say, 1/5, 1/6 of the mapping was correct. But in the end, if you want to go into this paper, the conclusion by the authors was that you can still, the result was worth the efforts, because they saved time in checking rather than doing this in advance. All this say, the project that I would like you to involve in, and is something that we will test in the next hour and a half in the practical activity, is a project that is called Care On. It's a project founded by the National Research Council of Italy, the CNR, and has, well, quite a list of details, but basically we want to define the best practice and defining the standards in boulder counting. And we want to involve people in this. We want to test if people coming, for example, for a winter school, so almost topic specific, let's say, or common people can contribute to this. Imagine what you can do if you have thousands of people counting boulders over the whole moon or the whole Mars or whatever, and they can give you reliable results. Then you can really focus on the processes rather than on doing time-consuming tasks.